Okay, so what we're going to do over the next several classes is we're going to have a lot of fun with Poisson regression. Today we're going to kind of start off in review mode and work up an old example that you've probably seen before in some of the early epi courses to kind of just motivate what we're talking about with the Poisson distribution, why we care about it, and specifically how it relates to counts and rates. We're going to talk through just some examples of that. And then we'll start by moving into what is the Poisson regression model. It's going to look a whole lot like other regression models you've seen, but it's going to have its own special properties. Okay, and we'll talk about what a no interaction model looks like. Interesting covariates, we'll just have to find out. It's that interesting. But we'll talk about that. And then there's some statistical testing in the Poisson regression model, what to do when there's problems with the model. Just as you've noticed, like every single model we've shown you has some Achilles heel where that doesn't work. There's some assumption that gets violated. And so there's going to be assumptions to violate as well with the Poisson regression model as well. The big one has to do with over-dispersion, which is really a lack of fit of the Poisson model, where the Poisson distribution fails to describe your data. And so we'll talk about what to do. There's kind of two remedies to that. There's force the model to fit, and then there's this thing called negative binomial regression, which often works well when there's over-dispersion. And then the last thing is we'll kind of bring it full circle, and we'll get warm and fuzzy when we do survival analysis with Poisson regression. And so it turns out in a very specific case that's actually often not that unreasonable, you can actually do a survival analysis with Poisson regression. And we'll talk about why you may or may not want to do that, or what there's some advantages, some disadvantages, and everything's got advantages, disadvantages, and this is going to be, again, we'll go over why you would or would not do that. So that's kind of where we're going here. Okay, so I always start this off with just a personal story. So this is where we are. Right here we are here. So this is the story of how I got into a car accident a few years ago. That's where we're going here. And so we're over here. There we go. Ding. And it's interesting that we're like a thing on the map, like specifically out of all the other buildings on Emory's campus. I never noticed that, but we're special enough to be a separate graduation hat. And so anyway, so this is the intersection of North Decatur and Claremont, right? Which is who here has witnessed an accident at that intersection? It's incredible. There's a lot of accidents. There's just some key intersections where there's just a lot of accidents. So these data are made up, but this is just to show the principle of why we care about the Poisson distribution. So let's say every month you have a busy intersection and sees 100,000 cars go through it. It's maybe too much. Actually, I don't know traffic data well, but let's say that's 100,000 cars go through this intersection. The likelihood of any given car getting into an accident is small. Like even in the most dangerous intersections, right, most cars make it through okay. Right? And let's say you have a very small probability, so 0.00002, really small chance, right? So here's my car, which was hit by someone running a red light in this flood intersection. So even though your individual probability is small, on average, stuff happens. And in this intersection, lots of stuff happens. Like if I say any given time, there is debris from an accident in this intersection, which is remarkable. And it was really depressing when my own car's debris stayed in the intersection for like 3 weeks, and I would go back through it, and like I'd see like, no, that was my light. There it is. You know, and so it was. They don't really clean the intersections either because this is Georgia. Anyway, so yeah, so this is my little soapbox. So anyway, so what happened here is the Poisson distribution in that you have a high frequency, low probability events equal. You could still have, on average, a lot of accidents happening, and these kind of situations, and these situations happen a lot of in health research. So, for example, what is if this was the true state of affairs, and you want to know what is the probability of seeing 3 car accidents a month in this intersection, which is probably, maybe it's an underestimate, frankly, right? You would need some data like this. You say how many cars go through the intersection, 100,000. We want to know how many accidents. We want to understand the probability of 3 car accidents when the probability of a single accident is this small number, right? And we know some ways how to do this, right? One way is an old friend, the binomial distribution, right, which is this this n choose k, p to the k, 1 minus p to the 1 minus p to the n minus k, right? This is all the ways you can arrange the successes and the failures, right? This is in BIOS 500 somewhere, right? Yeah, I hope so. So this is the binomial distribution. It's this thing that dictates the heads or tails, the yes or no's, the true or falses. When you have a fixed number of events, a fixed number of trials, so let's say 100,000 trials, and there's some probability, and you want to know what's the what's the likelihood of seeing 3 car accidents? And you say, oh, binomial distribution, tell me what my probability of seeing 3 or here it says 2 car accidents. I meant to say 3 here. Sorry. What's the probability of seeing 3 car accidents? And sorry, I'm getting some water. You plug into the binomial distribution, and you say 100 choose 3, which you do 100 choose 3, which is all the ways you can arrange in the 100,000 trials, all the ways you can arrange your 3 events, your car accidents, times 0.0002 to the 3rd power, and then 1 minus that to the 100,000 minus 3, or 99,997th power, equals 0.18. This is not very computationally nice, right? So if you put this into a calculator, it might get pretty upset at you. And some of these, right, this function can get pretty uncomfortable to calculate as well. So, if you could calculate it, and your computer could, it just might not like you, you would get that the probability of seeing exactly 3 accidents given this distribution is 8.18 or 18% chance that you'd see 3 accidents in that month given the kind of accident data, right? So, and then you might ask some other interesting questions. So this question was, what's the likelihood of seeing 3 accidents, right? Which is different than the likelihood of 4 accidents and so forth. You could say, what's the average or expected number of accidents in a month? And that's n times p. Right, that's another familiar property of the binomial distribution. So it's 100,000 times 0.0002 equals 2. So you'd see on average, the most common outcome in a given month would be 2 accidents. But by the way, you have an 18% chance of seeing 3 accidents, and there's some distribution around 2 of what you'll see with different likelihoods in a given month. So the binomial distribution is, usually in the examples that we use, we're not dealing with such rare stuff and such big numbers of trials usually. It's, a few hundred, or, you're doing these little probability games and doing rolling dice or whatever, and it's not 100,000 choose 3, but you can use it. And so, so here we go. Wow. These are rhetorical questions that now the computer's locked up. Okay, so here, do we have a way to model the binomial distribution? We have a modeling procedure for that, right? Binomial events, what do we use for that? It's like the first half of the course, one of the books. Logistic regression, right? So the logistic model, we actually don't get too much into it in the course, but one of the assumptions of the logistic model was that the probability distribution, given all of the covariates in your model, that your outcomes are following is binomial. And it's actually modeling a binomial process under the hood. And we actually don't spend too much time on that mathematical underpinning, but just like in linear regression, there's this normal distribution piece in the background that conditional on all the things in your model, the outcome is normally distributed. Similarly, in logistic regression, it's that conditional on all this stuff in your model, the outcomes are now occurring binomially or with some probability. And so you could, technically, imagine if you had data on intersections. You say you had, data on 200 intersections in Atlanta, and you had all these accident data. You can model the occurrence of accidents, let's say across all these intersections, or maybe you're looking at car models or something, and you can have covariates, and you can imagine a situation where you would model this kind of data with logistic regression. The thing is, though, does this look friendly from a computational perspective? Right, so you imagine you have your data is that there was 100,000 cars, and 3 of them got into accidents, and you have to model now basically 100,000 events in your data set in order to perform logistic regression. So it's a kind of computationally irritating thing to do, frankly. And I'll show you what this data set, I'm going to do a data set comparison in a few slides. The data set to deal with rare events in this way would require 100,000 observations, which is just not fun to do. So I'm going to talk about the Poisson distribution, which is an alternative distribution that, they approximate one another in the instance of rare events. So the Poisson distribution is much more manageable than calculating things to the 900, whateverth power, which is, again, not very fun. I mean, effectively, this is basically 1, right? This is more or less 1. This is more or less 1, to the very large power is still 1. But to get this exactly is not fun for you or a computer. So the Poisson distribution, and you've all seen this in places before, right? This is, again, we're getting to Poisson regression, so pardon the backing up a little bit. The Poisson distribution describes the count of rare events. It works well when we have a situation like we have now, where we have a big N number of events and a small probability on a given instance of the outcome occurring. And in this instance, the Poisson approximates the binomial. So we have rare binary events, car accidents, it's going to be disease outcomes soon. We'll have the skin cancer outcome coming up. So we have rare events, and the sum of them is going to follow this thing called the Poisson distribution. And it can be used to describe counts and rates and risk. And we're going to go through all of these, starting with really counts and rates. And this is the function that describes the probability of observing a certain number of total successes or failures of its car accidents, but a certain number of outcomes on the Poisson distribution. So it's the probability that y, let's say, equals 3 accidents. Is equal to e to the minus mu times mu to the y-th power over y factorial. And what are mu and y? Well, y again is the number of events that you're interested in, and so here, let's put it up with the actual example. So in our situation, where we were interested in observing 3 accidents. We want to know what's the probability of seeing 3 accidents. That's this y that goes in here. And there's this single parameter, which is just the mu, or really called the Poisson rate parameter. And it's the mean parameter. And it's really the expected number of events that you would think to see in some period of time. So we know from before, we said, well, we think that the mean number of events was 2, based on n times p from the binomial model. So we say if we think that on average we're going to see 2, what's the probability of seeing 3? You just plug into this formula, e to the minus 2 times 2 to the 3rd power over 3 factorial. This is mathematically much nicer than the binomial distribution, and you also get 0.18. So this is a different distribution. It takes the number of events that you're interested in and this mean parameter and then it can spit out the likelihood of seeing a certain number of events. So it gets you to the same place as the binomial distribution, except it is a cleaner formula and also has some theoretical differences under the hood that we'll talk about. One thing here is that, in the binomial model, in the binomial world, you're actually pre-specifying the number of as an input to the probability function directly, you have the number of trials. And in the Poisson model, there's kind of this idea that the count can go up infinitely high here. There's no upper bound on what you're doing. Here we're saying you can only have up to 100,000 accidents, and there really is no theoretical upper bound to the counts that you observe in the Poisson distribution. Of course, seeing 100,000 accidents would be very rare, but it's a different formulation and understanding of things. So the other mind shift that we need to think about with Poisson regression is this is a big one, and we're actually going to shift our understanding of what the unit of analysis is. So you can think about, in the car accident example, you can think about the unit of analysis in several ways, right? You can think about the smallest unit, which goes by other names in other fields and other courses. Sometimes it's called the observational or the sampling unit. Is the individual cars that are going through the intersection, right? That's the smallest unit at which stuff is happening, right? It's cars are at the intersection, sometimes someone smashes into you, right? That's what happens. And that's in a pure statistics course, it'd probably be called the observational unit, which is different than what's called the experimental unit. And the experimental unit is the bigger thing that we're measuring the process of to make inference about. So this is just a philosophical shift in how we're thinking. And that, in this case, is the intersection. We actually want to know, is this intersection going to see 3 accidents? We actually don't care about cars, per se. The cars comprise a basic process of the data, but the thing we actually care about is the intersection. And so in Poisson regression, we're going to be modeling this lower thing more than we're modeling the upper thing, which is the smaller units. And so, again, as we go towards real data, one of the major examples that we're going to use, in 2 examples from now, is this idea of looking at skin cancer in different age groups from surveillance data. And in that case, it's the strata of the surveillance data, 15-year-olds in Minneapolis, as a group is the thing we care about, and the fact that some of them get cancer and some of them don't, or whatever it is less of interest than that unit, the unit of the stratum that we're trying to describe the rates in. And so we're moving towards this idea of thinking, okay, well, we're going to describe what happens in the intersection as a unit, and by the way, 100,000 cars went through there, but we don't really care so much, which is different than a data orientation around measuring individual cars. Okay, so again, we're measuring this kind of more meta process thing in Poisson regression. Okay, so we're going to be less interested in the specific units that have the 0-1 events, and we really care about the counting process, this phenomenon of what happens at when we look at our hot air balloon at intersections, and we don't see the cars anymore, we just are counting, we're just counting the accidents. That's the level that we're zooming out to with many of the applications of Poisson regression. You're not always doing this, but most of the time you're doing this kind of reorientation of your thinking. So what does that mean here? So these are two different data layouts that you can do for the same analysis. So the left is the data layout for doing, let's say if you, again, were modeling cars going through an intersection, you want to know what kind of tires are most dangerous or whatever, or what kind of intersection properties were most dangerous. You would have, traditionally in this course, have done a data layout mostly like this, right? You have lots of cars, car 1 to 100,000, 0, 0, 0, these are all the crashes, no crash, no crash, no crash, 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 let's say, 3 crashes. Okay, that's obviously everyone inside these cars is totally happy and just the cars are smashed, but, because I'm not trying to be pessimistic, but, so but this is the data layout, right? We have a data set with 100,000 observations. Okay, and in here you usually have car level covariate patterns, right? You can imagine car 22 is blue and has tires like this and has a crazy engine or whatever it is. Your orientation might be to really look at the car level covariates and say what predicts a crash, and that's a logistic regression. That's a very logistic regression kind of thinking. For Poisson regression thinking, we're going to move towards this mode: a single row of data that looks at the total number of crashes. And this thing is going to be basically a denominator that's going to be used in the model. It's called the offset, and we're going to actually take the log of it. But the data really gets compressed into a single, this is this reorientation, it's a single unit, is just give me the data on the intersection. And it's 3 crashes out of 100,000 cars. And this is very big picture, 10,000 feet kind of view of what's going on. So in this orientation, covariate patterns specific to the cars get washed away here, right? You're not looking at, is it the big tires or the small tires or the people that don't have airbags or whatever it is. you're losing perhaps some of the individual data, but you might imagine you might have, you could still have multiple lines of this data for intersection properties, or you might stratify by types of cars, SUVs versus, small cars in that intersection. You might imagine some groupings of the data, but all of those little nuances around all the individual cars get washed away. Okay, but this is a unit suitable for Poisson analysis, and this is a layout for logistic regression analysis. So again, this is just a different way of thinking, and this, often in life, we are stuck with this kind of data, right? If you want to model surveillance data often, you don't have access to all of the individual people that had that cancer in that state. You have summary statistics that Sear spits out, let's say, or whatever it's going to be. And you may not really have data so suitable to this format, and you may want to really look at a Poisson model. We did very briefly talk about you can do logistic regression on this data layout. It was called the events trials format. But we're going to really focus on Poisson regression on this format of data. Any questions? Different unit of analysis, feeling good? Okay, so this is the example that I think has most certainly appeared in Epi 1, and maybe even in last, we did this in the spring a little bit, but I'm going to talk about it again, but we'll move into a Poisson regression way of thinking about it. So these are the male telecom workers. This is a lawsuit brought against their employer, New York State, based on data from 1976 to 1980. And so the idea here is you're up on a pole and you're experiencing all sorts of environmental exposures that are not good for your health. And here we have an observation that there was 2 cases of male breast cancer, so a very rare cancer for males, in this many men, 50,000 men, which corresponds to about 200,000 person years, which more or less makes sense because it's a 4-year observation period. So you see, so there was this observation of 2 cases of breast cancer in males. So 2 cases over this many person years, and if you put it over a standard denominator of 100,000 person years, that's roughly dividing by 2. And you see 0.97 cases per 100,000 person years. Okay, so rare for sure, right? 1 out of 100,000, 1 out of 100,000 person years is still a rare kind of thing. But based on the just general statewide rate for males, it was actually quite high. So imagine if you observed this in your employee directory, and then you went to some standardized tables for New York State for breast cancer outcomes, you would see that was 0.15 cases per 100,000 person years. So we're talking, here we go, a ratio of 6.5. This is standardized rate ratio, so 0.97 over 0.15, 6.5. So a 6.5 higher rate of breast cancer was observed in these telecommunication workers. Now, but your first thing when you look at this, you're like, yeah, but look, that's true, but it was only 2 cases, right? So this is still, is that really significant? Like, if it was 1 case, would it be much more comparable and who cares? And suddenly it's 2 cases and now it's something to get excited about, right? These are still very rare, and you might want to know, well, is this actually unusual? 6.5, sure, but let it play out a little bit longer and it's going to kind of balance out, and this is a very rare process, right? We only actually saw 2 cases on the ground here. So you might say, well, we need a way to test whether this is, whether this is a truly unusual observation, right? And the way we would test that is with our friend the Poisson distribution, right? And you might formally state it below here. So I'm using this little gamma here for the rate parameter. So we have gamma hat. Lambda, at TC for telecom workers. The rate parameter is is 0.97 per 100,000 person years. We want to know, is it significantly different than the rate observed for New York State, of 0.15. Okay, so if you want to know whether what we observed is significantly different, we're going to go to the Poisson distribution. We're going to do something like this. We're going to say, we think that this is a rare event, right? Men getting breast cancer is a rare event, and we're going to assume it's Poisson distributed. Why is that? Because the probability is very low, and the N is very high. We had a lot of person years of observation. A lot of observation time for a very rare thing. We think that this distribution dictates what goes on for male breast cancer. Okay, so what would that Poisson distribution look like? Well, the expected number of cases, the mu parameter, that's this other thing that the Poisson distribution needs. We might estimate it from the rate observed in New York State amongst all males times the person time in the telecom workers would give you the expected number of cases in telecom workers if they were just like the rest of New York State. That was a mouthful, so I'm going to go back and dissect that. So if the telecom workers in their 200,000 person years behaved, if they had the same disease outcomes as the rest of men in the state, you would expect that they would have 0.15 over 100,000 times that many person years, or 0.31 expected cases, right? So they said that in New York, the state, the rate is this, but was 0.15 per 100,000, but we actually observed this much time of male telecom time, so it's basically twofold. So we would expect that in the instance where the telecom workers were the same as New York State males, we would expect to see 0.31 cases. But we saw 2 cases, right? That's the problem. We saw 2. We should have seen maybe 0 or maybe 1, or on average 0.31. Something like we saw 2 is really the issue. So under the null hypothesis, we saw under the null hypothesis where this group behaved, or like a Poisson distribution, like the rest of the men in the state, we would see 0.31 cases. This thing is the mu parameter for our Poisson distribution under the null hypothesis, that we would have expected to see 0.31 cases. Okay, so we had to compute this 0.31, we had to compute by taking the rate observed in the state and multiplying it by our person time gives us the expected case count. Okay, so these are really the 3 pieces that we deal with Poisson regression. There's or one of the 3 of the key pieces. There's the person time we have, and then there's the rate, this kind of null hypothesis rate, and then the expected case count, which is the product of the 2. This thing is the mean and the mu piece that we're going to use in our Poisson distribution. Stating the null hypothesis this way is really the same exact thing as stating it this way, right? We're multiplying this rate by some fixed number to get 0.31, but saying that our null hypothesis that we should have seen 0.31 cases is exactly the same as saying our null hypothesis is that the rate is 0.15 per 100,000. Right? There are 2 ways of saying the same thing. And this interchange between a case count and a rate underlies all of Poisson regression, and we're actually going to state the model both ways. You can state it as a case count way, or you can state it as a rate way. And they just differ by this thing, which is person time. Right? But this is not that important, actually. We multiplied the rate by our person time to get our expected rate, but this is relatively unimportant and not really interesting to us. This null hypothesis is equivalent to this null hypothesis. This one is kind of data specific. If we observed another 100,000 person years of time, this would change, right? The expected number of cases would change. But this would not change, right? The rate, the null hypothesis rate would still be 0.15 per 100,000. And so we're going to make a hypothesis test that says, what is the probability of seeing 2 or more cases given that our null Poisson distribution, of mean rate 0.31, mean parameter 0.31. Okay, and we have all the pieces in our Poisson formula to do this. So we're going to say, we're going to assume that our males, telecom workers, behave like New York State, and we're going to say, what's the likelihood of seeing 2 or more cases? Okay, and then it looks something like this. We say that the probability of seeing 2 or more cases is 1 minus the probability of seeing 0 or 1 case. That's the easy way to do this. Otherwise, you're going to be infinitely counting 2, 3, 4, to up to you get tired. So the easy way to do it is you do 1 minus the probability of 0 or 1 case. This kind of thinking probably came up a bit in BIOS 500 when working with these distributions. That is sometimes easier to go in the other direction. 1 minus the probability of 0 or 1 is often easier than going the other way. And so you use these, you make little, here we go, 1 minus the probability of 0 and 1 minus the probability of observing 1 case. These little pieces in here are little Poisson distribution probability functions. So here we have e to the minus 0.31. This is that mu parameter times 0.31 to the 0. That's 1 over 0 factorial. That's 1. And then here, this becomes e to the minus 0.31. So this is the probability on the Poisson distribution of observing 1 case given you expected to see 0.31 cases. Right? And this is, again, that formula that we showed. And what you see here is that the probability of observing 0 cases was 0.73, which makes sense because the expected value was 0.31. So that means a lot of the time you're going to see 0. If your average value that you expect to see is the count that you expect to see on average is 0.31, you can't see a third of a case. So you're going to see a 0 a lot. Sometimes you're going to see a 1. You're going to see 1 case 23% of the time. And then 1 minus 0.73 minus 0.23 is 0.04. So what this means is you have a 4% probability of seeing 2 or more cases given that the telecom workers had this null situation of being like other males in New York State. So remember, this is that weird dance with hypothesis testing. We always do this backwards thing. We assume this null case, and if the null thing is so unusual, we reject the null hypothesis and say, I don't believe that. I don't believe the null. So here at 0.04, the probability of 0.04, if your alpha level was 0.05, you would reject the null hypothesis and say, actually, I don't buy that the telecom workers had the same rate parameter as the males in New York State. They must have had something different. And that's where the alternative hypothesis comes in. You say, I don't believe, this is unusual. I should not have seen 2 because it only would have happened 4% of the time. This is unusual. I'm going to reject the null hypothesis and believe that the males, this group has a special different rate. Right? That's kind of, probably a higher rate parameter, right? And you set up, and that's really what you're saying here, that we believe that the rate parameter is higher for these workers because this is an unusual outcome for this group. They should have seen probably 0 or a 1, and we saw a 2. So this is that standard kind of hypothesis test thinking, where we assume a null thing, and then we show that, in this case, that the null hypothesis is unlikely. Is unlikely to be the case. Okay, so this is again using the Poisson distribution. So we took an expected case count of 0.31. We figured out, we saw we had 2 cases, and we said how unlikely would this have been? And the answer is it would have only happened 4% of the time. In all those alternative universes of 1976 to 1980, right? Of course, which we only saw once, but that's kind of the idea here. So we say they have a different, we saw a weird number of cases, or we saw, a different rate. Again, this idea of rate and cases are interchangeable here in the Poisson world. Okay, so this was just a hypothesis test on a single rate, right? That wasn't very interesting, right? In some sense, like we just compared a single observation on a group. Again, we didn't measure individual males. We have an observation on a group of males, and we compared it to an external number of 0.15. Right? There was a single group, though. It was just the men on the telephone wires versus some static number in New York State of 0.15 per 100,000. So that was a single rate. And then in our line of work, we're usually more interested in comparing rates, right, and making inference about groups versus each other, and often for causal inference purposes. And so we really want to be able to compare groups, right? And we've seen this before. We definitely talked about this in the spring, because we made tables like this, right, where you have a 2x2 table where you have case and denominator data to make comparisons in the rates, right? And so we could compare groups with different amounts of person time by doing things like computing the rate ratio, right? And so here's data, I think I'm not sure if this might be real data on California. Here's data on California, 7 cases and 550,000 person years of time. And then here would be the rate ratio for California versus New York, right? You do 7 over 550,000 over 2 over 206,000, you get 1.31. Right? So this is EPI 1 and 2 kind of stuff, right? You're comparing two rates, and you get a rate ratio, and then there's even lots of methods. There were several methods talked about in the spring for getting this. This is the normal approximation method for getting the confidence interval, right? So you can use this e to the log of 1.31 plus or minus 1.96, and then square root of the 1 over the sum of the 1 over a and plus 1 over b. I'm not making you know this now, but this hopefully rings a few bells, right? This idea that you have a 2x2 table and you can come up with a confidence interval for the rate ratio. Okay, so this is really great. This is very interesting. There was the exact method for doing this also covered, which really dealt with the binomial and Poisson distributions both. Except that this method, this way of looking at the data really isn't controlling for any covariates still, right? We're just doing a basic kind of 2x2 table, unadjusted comparison, and we really can't get fancier right now with the methods that we've entered the course with for dealing with these kind of rate data, right? Because like, what if you had 20 states of data and you had covariates on the states? You know, some states have different types of sunshine, and other ones have different heights of the electric wire, or different charges. I don't know, whatever's going on, the electric wires is different, or different workforce protections that are in place, or whatever it is. There might be state-level covariates, or interesting covariates, and other things that you might want to adjust for, or model, or talk about that this methodology doesn't let you do. And we really would like a regression method that lets us adjust for factors of interest when we have these kind of data scenarios. And that's where we're going here. So what we're going to do here, and I'm just going to jump down to the bottom for a moment, is we're going to do this. We're going to model the rate as a function of covariates. Okay. So we're going to move towards modeling this kind of 2x2 rate data. But now it's not going to be two groups anymore. We're going to model rate data for states or whatever units we care about, intersections, and we're going to be able to look at their covariates in a regression model kind of way. Okay, and this just again kind of goes over some of the interplay that's a little confusing perhaps in the Poisson model. We observe this is the relation. This is the mu parameter of the Poisson model, and we said it's the expected value of the counts, and it's also more or less equal to the rate times the time, the rate times the person time observed in a given population. So if you have a 0.15 per 100,000 is your rate times this much person time, that's the expected number of the count that you would observe for that population. But what we actually observe in our data set, of course, is usually just the counts, right? So what do we usually have as consumers of data in the epi world is we usually we don't directly observe the rates per se. We observe this thing called the counts, right? We go out in the world and we count cases, how many people, how many cars, how many cancers, how many whatever. And we would like to make inference about the rate, right? We actually don't care about necessarily the specific counts that we measured. We measure the counts as a way of talking about rates, if that makes sense, right? So we need to kind of reverse this equation a little bit And imagine, here's this, we have the mu is the expected value of y, and that's the rate parameter times person time. We really want to solve for the rate, right? Because we want to talk about the rate. We want to model the rate, sort of. That's the thing we care about, and that's really the expected value of the count over time. So imagine this equation, you divide both sides by the time, and so the expected value of the count over the time is the rate. Okay, this is just manipulating the same three things. But the thing we really, we observe the counts, but we don't care about them. The thing we really, really care about is the rates, and we really prefer to model the rate as a function of some covariates. That's what we want to do. That's the name of the game, because the rates and the rate ratio are these universal things that we care about. The specific counts in a given population, I don't care about. You might care about, maybe you care about a very specific, you want to estimate 2 male breast cancer cases in New York State, but you want to make a more broader understanding about the rate of cancer in New York State. The specific 2 men that were observed in that period are less interesting than what is going on in New York State, what is their rate in general. And so we look at the counts, but we're trying to really get towards the rate, and the interplay between that is you divide by time, the counts over time gives you the rate. So we're marching towards this thing, which is Poisson regression. We're going to model a model that looks like this. The rate parameter is is the expected value of the counts over time, and then is e to the usual kind of linear function here, beta naught plus beta 1 x1, beta 2 x2, and so forth. And these are going to be covariates on the groups, on these big units of measurement that we care about. Is it states? Is it intersections? Is it whatever? These are going to be covariates that let us explain and explore what's going on in these observations of counts and rates. Okay? There's going to be an alternative formulation of the model that solves not for the rate parameter, but the mu or the expected value of y parameter. Remember, those are the same. Okay, so you can write the model in terms of the rate or in terms of the count. The theoretical way of talking about the model is the rate formulation. This is the one that makes sense. But what SAS does is this formulation, the count formulation. So that's why we're going to have to do both. This is similar kind of sort of to how logistic regression has the logit form and the probability form of the model, where you have 2 dueling ways of looking at the model. Poisson regression is going to have the rate form and then the count form. I don't have good names for them yet. They're very similar. They only differ by one thing, which we'll talk about. Okay, so if this is the function for the rate, by the way, if you take the log of this, what you get is that the log rate is this linear nice function, right? Because the rate is just e to the linear function. So you take the log of both sides, and you're left with you have a model for the log rate. Okay, so this is a modeling framework that's going to let us look at more than just a 2x2 table of rates. We're going to look at, you can look at 100 different jurisdictions and compare them on interesting things and say, wow, is it the protections that state has that's causing the lower cancer rates in their male telecom workers? They're wearing leaden jackets or whatever it is, or is it, you can explore all sorts of interesting things. You can explore the effects of time. You can do all sorts of cool things that you couldn't do when you had just a 2x2 table. And this is the modeling framework for that. And again, this is really, what's letting us do this is that it's a model of rare binary events. So just to zoom out, this is kind of our universe. I haven't put the Cox model in here, which is a little bit different, but this is just another case of what's called a generalized linear model, which is a model that after you sufficiently manipulate it, looks rather linear and like a linear regression model. Right, so here's the linear regression model up on the top. The expected value of y is this intercept plus beta 1 times x1, beta 2 x2, and so forth. This is the linear regression model. The logistic model is that the log of the odds of y. Here I'm doing I'm saying expected value of y, which is the probability. It's the same. They're interchangeable. This is the log odds of y is a linear function. And then here, the Poisson regression model is that the log of the rate parameter is a linear function as well. Okay, whoops. So we're showing a different model, but it's really a variation on a theme that kind of flows throughout all of this, through our course. And what's going on here, what differentiates the models are two pieces here. One is called the link, and one is the distribution of the data given the covariates in the model. Okay, and the link is the function that you have to apply to linearize the model, basically. So here, let's just jump down to Poisson regression. In order to have the theoretical form of lambda is e to the beta plus beta 1, x1, and so forth. We had to take the log, the natural log, and that linearizes the function. So that's called the log link. In logistic regression, it's called the logit link, because it's a logit function. Otherwise, we have that nice and ugly 1 over 1 plus e to the minus, that whole fun. You had to apply the logit function to linearize that. And then the linear regression is called identity, which is just, y equals x, the same thing. So there's nothing that do nothing is what this means, and it's a linear function. And then the other piece that distinguishes these is the distribution of the data around this function. So remember, in linear regression, the data are normally distributed about this linear function. That's kind of the whole point. That's the normal distribution assumption. In logistic regression, the data are binomially distributed about this function. And in Poisson regression, we're going to assume that the data follow a Poisson distribution around this function as well. And of course, the types of data that you use these for are different. So linear regression is continuous, right, from negative infinity to infinity. In logistic regression, you can only observe your y as 0 or 1. That's it. And in Poisson regression, the data take the form of a count that really goes up to infinity. There's supposed to be an infinity sign there. So it's a different kind of thing here. It's the count of binomial events, and that is in a sense kind of infinite. But remember, as we started at the beginning, there's this interplay between the Poisson and the binomial models where this is the count of a binomial process. How many car accidents happened, right? That's a heads or tail. Whether a given car gets into an accident is a heads or tail kind of thing. It's a dichotomous outcome. And the sum of those dichotomous outcomes becomes this count. So these are sort of related, even though one's a count and one's a 0, 1 variable. So again, the link is the function that's applied that linearizes the model, and the distribution is the distribution of the data given the x's or given the function, really. So that's just kind of zooming out. Like this hopefully feels a little less scary when you line it up and realize, like, oh yeah, this is just another variation on a theme here that lets us model different kind of data type. So what we're going to use in parts of this are a slightly different notation for these subscripts. This is what the book uses. This is not like what you have to use in life. This is just it's helpful for this course. It's helpful in the book. And because oftentimes the data that's used for Poisson regression needs kind of some bookkeeping to it. And so that's why we have this I and J subscripts. But you don't need to have this subscript notation, just like you don't need to ever write EVW. But this is a helpful way to organize the information. And we're going to say here that, so we have I's and J's on everything here, and that the I and J is the ith count on the jth subgroup, which are going to really be covariate patterns. So we're going to get back to covariate patterns here. And that, so you can imagine that you have, we're going to have a subgroup might be New York State. Let's say New York State. We observed the number of, cancers in New York State. And we observed different years of data, 4 years of data in New York State in your model, and that's 4 pieces of data in your model. New York State in 1976, 77, 80, or whatever, The years would be the ith counts on potentially on the jth subgroup. So what you'll see in some of the examples is that we have a need to kind of deal with repeated information on the same unit. And so we're going to sometimes use this kind of subscripting notation. And you use it to terms in the model, for the data in the model. So xij1 is the, variable 1, whatever it is, if it's, I don't know, state law, whatever, for modeling the breast cancer piece, that's the variable 1 on the ith count on the jth subgroup. Again, this is just a notation system, but we'll see it here. So here's an example that we're going to talk about a bit, which is data on non-melanoma skin cancer in 2 US cities that differ in terms of their sun exposure. So that's kind of why the comparison's of interest. So here's some summary data that you might see if you went to the CDC website and you grabbed some data. It might come to you in this kind of format, right? And you'll see here we have age strata by city, right? Dallas, Fort Worth, Minneapolis, St. Paul. And we might see cases, total population size, so the denominator effectively, and then the rate, which is just the cases over the population size. So, and this is going to be this is per 100,000 here, rate per 100,000, right? So you might see a table that looks like this, and then you might see a column at the right that says rate ratio, or RR, right? And 3.8, 2.0, so forth. Okay, so this is a great data set for Poisson regression analysis. Summary data. And what you can see here is we have, using the IJ notation, we have only one observation on every city-age combination. We have 16 pieces of data here, really. We have 8 age groups on Dallas-Fort Worth and 8 age groups on Minneapolis-St. Paul. So we really have a data set that has 16 units of information, and they belong to really 16 different subgroups, potentially, at least the way we're going to model it, where we have every observation of case, every case population rate kind of line here can be characterized by its age group and its city, and we have 16 observations of this. Right, and what's important to know here is that this column is the only thing that's really observed, right? That's one of the things with a lot of surveillance data. The only thing in the data that's new data is the cases, and the population usually comes from census data. These are usually administratively determined values that are external, and this is the person time. And this really exemplifies that the person time is something we don't really care about. It's something that's in the way. We really care about the rates. We have to measure cases in order to measure the rates. And this thing comes from the census, and we don't really care too much about it. I'm speaking very colloquially about it, but that's kind of the order of events of things we care about in all of this. At the end of the day, we care about the rates and the rate ratio. We have to measure cases, and this comes from the census. So, but that's really important to remember. What is the true piece of information that we measure? It's really this thing. And this is the thing that the model is going to most heavily focus on using. And here we go again. So I just labeled this by the pieces here. So this is the YIJs, is the cases, and then person time, and then the estimated rates, the lambda IJs. Okay, so surveillance data are great for potentially for a Poisson regression analysis. Okay, so you look at these data again, and then you say what could I do if I had something better than a 2x2 table to look at these data? Well, I might ask a lot of interesting questions. Okay, one of them is, these rates, if I just eyeball them, they feel kind of bigger than the rates. The Dallas rates feel kind of higher than the Minneapolis rates, right? If you look along each row, every group is consistently higher, and it's about 2 to 3-fold in these age groups. The rate ratio on the rows summarizes that. And we look at these and we say, there's kind of the city effect. Kind of doesn't look so fun to be in Dallas relative to Minneapolis because of the skin cancer problem, or whatever you're going to say. Like you feel this kind of thing, and you might want to quantify and make statistical inferences about that. But then there's this other thing, which is that, look at these 2 other interesting observations. The rates change with age, right? So the young folk, 2.2 per 100,000, going all the way up to pretty high rates in the older population, right? So up to we're looking at almost 1 per 1,000 here. So there's a big gradient along age, But by the way, the age distributions are also different in the cities. So what that suggests is that a crude comparison of the two cities is probably unfair because of confounding. Right? That if I told you like that the rate ratio is just 2.1 on this summary row, you would say, no, that's not right because the rates change with age and there's a different age distribution. I feel like you've got confounding going on. You can't compare these two because they have a different age distribution. Right? It looks like if you look at the population, if I don't have the population percents in here, I want to say that the population's younger on average in Minneapolis. If you look at where this is, the age distributions are different. I'll say that. So you might say, geez, I can't just compare on this row. I need to control for age confounding in all of this. To make a fair comparison, I want to control for age. And then you might look at this other thing. Look, the rate ratio might change with age too. Not only are the rates differing by age, but look at the rate ratio. In the youngest group, it's a fourfold effect almost, maybe. Obviously, it's small numbers. And then it's a 3 to 2 something. And then that looks like the increased burden of being in Dallas maybe declines across age. Here it's 1.8-fold the risk to be in Dallas versus Minneapolis versus something else. So you might say, geez, is there an age by city interaction that move from Dallas to Minneapolis when you're young and come back when you're old because the skin cancer risk declines? Or I don't know, you can make some interesting story about some great migration between the two cities. But it looks like there might be something going on and you might want to test for that. And the old methods that we've shown you in this program till now don't let you test that. What's a method for dealing with the age confounding problem that's not regression? We have done that before. Standardization and stratification, I guess, but standardization, which involves stratification, right? You can do some kind of process where you stratify and then recombine these to equalize the age distribution in some way through the indirect method or the direct method, and that's a way to deal with the confounding. But that has a whole lot of limitations too, because you're doing stratifying analysis. You can't control for too many other covariates. What if you had data on 20 other covariates here? We're going to have a problem. And the other piece of that standardization does not deal with interaction. So when you do standardization, you're getting an adjusted single best number. You're turning the 2.1, which is now an unfair comparison because of age, you're making it a fair comparison by fixing the age distribution problem. And now you get the right answer is 1.7 or whatever it is. But if there's interaction or effect modification, the city effect is modified across age or whatever you want to call it, the standardization won't work either. And so now you might be in this business of Poisson regression. And so we're going to talk about what that model looks like today. So we looked at this earlier. I put some more the IJ subscripts in. This is the log rate form of the Poisson regression model, okay? And it's going to be the log of the rate, sub ij, is this linear piece. And you can even write it shorter as the intercept beta naught plus the sum of all the betas times the x's. This is similar notation to what we did in logistic regression. And this thing, we have the estimate of the rate or the actual rate. The actual rate is the expected value of the counts over the person time, and that's the expected rate in the population. What we observe in our data are actual accounts, the y sub ij's over the person time, and that's the estimated rates for each count in each group. So these are two pieces. This is the estimated thing, and this is the real thing. Okay, so we're going to make a new form of the model using some of these mathematical relationships. I'm not just regurgitating them for fun. So here's this piece that we have that the rate is the counts over the person time. If I take the log of either of these two pieces, this is showing taking the log of the first line or the log of the second line, you get when you take the log of a fraction, it's the difference of the two logs, right? That's one of our nice logarithm rules. If I take the log of the rate of this theoretical quantity here, I get I can solve for the this is, here, I want them to come up one by one. Okay, here's log of the rate, and it's the difference of the log of the count, expected value of the counts minus the log of the person time. That's just splitting apart this fraction. You could rearrange the pieces here. So rearrange the pieces, move this over to the left side and move this over to the right side. And then there's going to be a divide by one piece. So you have to do some pieces, or you can add, or just add the offset to both times. That's the easier algebraic way, is you add log of person time to both sides of the equation and then flip it. And isolating this, you get that the log of the count is equal to the log of the rate plus the log of the person time. Okay, so you go from this expression to this one, just with some algebraic manipulation. The log of the count is the log of the rate plus the log of the time. Okay? So you can get an alternative version of this model by using this relationship. Plug in this blue box, the log rate form of the Poisson regression model, into here, where it says log rate. And what you get is a different model that's now the log of the expected value of the count, not the rate, and it's the same exact thing plus the log of the time. Okay, so two versions of the same model telling you, but they're modeling two different things. One's modeling the rate, and one's modeling the count. Okay, but it's the same information. You get the rate by dividing the count by the time. It's just the same information. And this is an alternative form of the model, and it has this little thing hanging out, which is all of the person time. So on every row of data, you got to feed in as an extra variable this thing called the log of the person time. And this actually becomes a new variable in your analysis that we're going to use, is you use the person time, right? You take the log of it, and you actually include it in a fancy way as a term in the model. You don't write it exactly on the model line. You use it, you have to specify it in a different spot. In the proc gen mod. This thing is called the offset, okay, and it's this like correction factor that you got to put in for the person time. It's not really data. This is the census thing. This is this thing that we need, that's in the way that we got to do to get the right denominator to get the rate. The real data is in the counts, and this is a nuisance piece called the offset. So this is the more theoretical way of writing the model, and this is an alternative way of writing the model that has the person time in here explicitly. It used to be in here baked in as the denominator of the rate, and this version splits out the counts from its denominator. And the reason this one is favored is because A, this is what SAS is going to use as its representation of the model, and like we said earlier, in the world, you never actually get data on the rate, right? You don't like go into New York State and say, what's the rate of breast cancer? Right? You actually go to a hospital and you look for cases of breast cancer, or you do something where you look at the counts. And then you say, oh, divide the counts by the denominator, the census total, and now I have the rate. So the thing that's observed, this model corresponds into stuff that you observe. You observe the count and you observe the person time, and that lets us model the rate. That's the beauty. That's the beauty of it all, is that we really care about this theoretical model, but we never observe this rate thing, really. We most proximally observe the count and the offset. So this is the better way to use the model. Okay, so here's one model. Here's a basic model that is a model that looks at the effect of age and city with no interaction. We'll get to the interaction model using that. Using this data set here, the 16 rows of data table. Now obviously, in SAS, you need to stack this. We're putting it next to each other because it's pretty, but remember, SAS is not going to want two things next to each other. You would actually have 16 lines of data. You'd have, and I think this is actually, I hope it's coming up. Here it is. This is what that actually looks like in SAS, right? So you have 16 rows of data. The first chunk here are city 0, which I think, let's go back. I don't remember which one is 0. That's Minneapolis. So 8 rows in Minneapolis, 0, 0, 0, and then starts Dallas-Fort Worth. They're stacked on top of each other. And the real meat of the data is the case counts, which is this column. And then you have this thing over here, which is the denominator data, the population size of that group, that age group in that city. And then here, these we'll get into in a moment what these other variables are. But this is the data layout that we're talking about for the 8 age groups. Here's age group, by the way, on the rightmost column, 1 to 8. So, so one way you can model this doesn't have to be the way to model it, is you could make, you have a model where you have the log of the rate is alpha, the intercept, plus beta times exposure, and plus 7 dummy variables to represent 8 age groups. Seems reasonable. We're not treating age as continuous, we're going to treat it as categorical. Here the exposure is which city you're in. So yeah, 1 if Dallas, 0 if Minneapolis, St. Paul. And you have 7 indicator variables to represent the 8 age groups. So that's what these were here. These were the dummy variables for the age groups. You can also use a class statement on age group, which we'll see. But let's say we explicitly put in age groups. I don't have a good explanation for why it's U. I'm actually conserving the notation that was in the textbook here. But we can call this V, right, which is our usual here. But here we're using U. And so here you might want to say, well, what's the adjusted rate ratio for Dallas versus Minneapolis, Dallas-Fort Worth versus Minneapolis-St. Paul? I'm sorry, I'm not giving the sister cities their due. I keep saying Dallas and Minneapolis. So what's the rate ratio for Dallas versus Minneapolis controlling for age, right? And so for any given age, let's say for a given age K, it would look something like this. Here's the rate for, let's say it's age group 2 or 3 or whatever. That's what I mean by K. For the rate for Dallas, it'd be e to the alpha plus beta times 1 for Dallas, plus the single indicator variable for that dummy group is 1 times gamma for the that specific group for age group 3 or whatever. And then here is that expression, e to the alpha plus beta plus gamma sub k. That's the rate, the estimated rate for Dallas. The equivalent rate for that same age group in Minneapolis is e to the alpha plus gamma k, because this city variable is 0. Okay, so this starts feeling like odds. This looks like this is the same expression for the odds in logistic regression. Okay, and when we take the ratio of odds, remember stuff cancels out. Well, lo and behold, in the Poisson model, the rate ratio for Dallas versus Minneapolis, is going to be the rate over the rate, and that's e to the alpha plus beta plus gamma k over e to the alpha plus gamma k. This, all sorts of stuff cancels out, and lo and behold, you have e to the beta. This is the same algebra exactly as the logistic model. This is absolutely 0 new, except that we're now modeling the rate using this e to the alpha business rather than the odds. And we take the ratio, and things conveniently cancel out when we're controlling for a given age group, and we get e to the beta now represents the rate ratio in the Poisson regression model. Okay, so again, this is going to, as you might imagine, this is going to get more complicated. Once you have effect modification, it's going to get exactly funky in the way that the logistic model did, where you now have to deal with the terms that involve the effect modification. Right, you're going to have to deal with it's not just going to be e to the beta anymore. You're going to have other complicated stuff to deal with, and we'll talk about that and what that looks like. But in general, this is really nothing terribly new conceptually. But we're now modeling the log of the rate parameter. And again, in SAS, the way we do that is we feed it counts and we feed it offset variables, and it is modeling the rate, but we feed it that information. So this is kind of what the code for that looks like. We're going to now be using proc genmod. There's no proc Poisson, doesn't exist, not going to exist. There's this thing called proc genmod, and genmod can fit a whole lot of different models. In fact, you can use it to fit every model in the course. I don't think it will do survival though. So we can do linear models and logistic models all you want. And the way we do that is you change the link and the dist distribution, just for distribution. you can manipulate its model statement to fit anything. You can say link equals logit, dist equals binomial, and lo and behold, you just made logistic regression. Or you can say link equals identity, dist equals normal, and you get linear regression. So, and it can do a whole lot of other fancy distributions as well. GenMod is a generalized linear models package. That's what it's called, a GenMod, and it fits this whole family of regression models. So if I wanted to fit that model on the previous slide that we're talking about, which was just looking at city and age group, you got to first do one thing, which is you got to make the offset variable here. So you take, imagine someone gave you this skin cancer data set. It's going to look something like this. You're going to need to manually compute the log of person time because time itself isn't what the model needs. It needs, from what we saw here with this algebraic manipulation, we need the natural log of time, of person time. So you actually have to manually create it. SAS won't do it for you. You can't say offset equals time. By the way, SAS, take the log of it yourself. It won't do that. You have to do it in a data step here. And so you can make a variable, let's say n was the number of people. This is the natural log function in SAS. You have to say make up whatever you want to call it here. I did ln underscore n. This is going to have to appear on the model line after the slash as a thing that says offset equals whatever you want to call it. You can call it hot dogs or whatever, veggie dogs. But it doesn't matter. It just has to be consistent with what you did in your data step. This is going to be the offset variable that you need to have. If you don't do this, you will get the wrong answer. So in the Poisson regression world, we're going to have to specify after we do our model, link equals log, dist equals Poisson, offset equals whatever we've made before. So after we do that, it's business as usual. Model cases. Cases is the count. It's the counting variable now. It's not binary. It's not continuous. It's a count. Equals city, and then all of our indicator variables, those dummy variables for the age groups. Or my preferred method, which is tell SAS to figure it out, which is you have age groups 1 through 8 coded 1 through 8, and then you say use the class statement and say class age group, and SAS is going to go make the dummy variables, and you're going to get to the same place in the end. So it's pretty straightforward. We're going to do a few fancier things. We're going to talk about the output. Yeah, let's not even go here. It's late. We're going to go home. But this is where we're going here, and we're going to get cool things coming up, which we'll talk about. Thanks.